So the amount of electric flux going through an area is equal to the electric field strength times the area. However, if the area is not perpendicular, then it turns out to be a dot product, and you have to bring in that cosine term. So finally, we get to a more complicated system. Let's say you have some funky electric field, looks something like this. One going up here, maybe another line coming down here, and then maybe a line in here. Who knows what charges are out there that's forming this invisible force field? But this is what the electric field ends up looking like. And then let's say we take like a handkerchief, some kind of like surface, but it's not just like a piece of paper. It's like a wrinkled handkerchief that's maybe been used and has a little stiffness to it or something because it has some curvature or something. So we have this like handkerchief. That's about the worst looking handkerchief. I got to try that again. Some area, like a handkerchief. Is that how you spell handkerchief? Put a D in there? Hand. Like that? So this area, that's correct. Thank you very much. This area is it's going to have flux going through it. And if we want to calculate how much flux is going through that area, we're going to have to break that handkerchief area up into little baby areas. Like a little area right there. This is an infinitely small little piece of area. And that little tiny area has its own little baby normal line coming off of it. So let me make this a little bigger here. And I'll draw in the little normal line. And we're going to put a little unit vector in the direction of that normal line. And that's called n with the roof. And we're going to make that little baby area into a vector quantity by saying that dA vector is just the area dA times the unit vector going in that direction. But now the electric field at that particular place might not necessarily be going perpendicularly through that little area there. So there might be an electric field line going like up like that. through the area. So right where the electric field crosses that little piece of area, I have a little electric field strength right there. A little piece of the electric field. dE, and that is a vector quantity. And then the amount of flux going through that little tiny area would be d phi, and that would end up equaling dE times dA, a dot product. Or you could say d phi, and phi turns out to be a scalar quantity, because the answer from a dot product is a scalar product, is a scalar quantity. Or we could say the magnitude of dE times the magnitude of dA times cosine theta, where theta is the angle between the electric field strength and the normal line to the area. And then if I want to get the total electric flux through that area, that handkerchief, the total flux would just be equal to the integral. But this is not an ordinary integral. This is an integral over an area. Usually you don't get into integrals over an area until like Calc 2. So I'm not sure if you have done integrals over an area yet. Sometimes integrals over an area are written as a double integral. Because like the integral over x and the integral over y. But you don't have to write it as a double integral. It's just the integral over the whole area of the handkerchief of the electric field. And you know what? I don't even think we're calling that dE. It's whatever the electric field strength is right at that. So this is just an E. Well, you know what I wanted to write first? Phi is the integral of all of the d phis, the sum of all the little d phis, which is equal to the integral from 0 to a of e dA, e dot dA. Or we could say the integral from 0 to a of e dA cosine theta. So that's the most formal formula for calculating electric field flux. Electric field, or electric flux. may, oh my God, this is so complicated. You know, in the end result is something very simple and beautiful. You're going to love it. Any questions, comments on this? All right, so let's take a look at another situation here where we have a point charge. Q1. Positive little point charge, Q1. If I want to imagine the invisible electric field around it, I could pretend to put a little tiny tipsy, tiny imaginary positive charge. If I put it over here, it would be going up this way, 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 this way, this way. But remember, it's a three-dimensional picture. There's electric field lines going like in every direction, not just the XY plane, but in the XYZ space. Now, this time, instead of using a handkerchief, I'm going to use like a potato sack, a closed area. As a matter of fact, I'm going to make that potato sack actually like in the shape of a ball. So my Gaussian surface, the surface that I'm going to analyze, is going to be like a sphere surrounding this charge. And I'll draw like I'll draw, you know, it's a sphere. This is three-dimensional here. So this right here is like a surface area around that charge. It's called a closed area, like a closed potato sack. And what I want to do, folks, is I want to calculate how much electric flux is going through this closed area. It's called a Gaussian surface. And I want to calculate how much flux goes through this Gaussian surface. And let's say the radius of this particular sphere is r. Well, here we go. I know that the amount of flux going through that thing is going to be the integral of all of the little pieces of flux, which is equal to the integral of the electric field strength through each little piece of area times cosine of theta, 0 to there. So my little pieces of area, I could take any little piece of area, like, so maybe I'll take a little piece of area right here. So that's going to be my little dA right there. But due to symmetry, and that's where Gaussian surfaces always get, you know, that's how they always get set up. They get set up so that symmetry is a huge plus here. Due to symmetry, since I'm choosing a sphere, what do we know about the electric field direction at that point and the direction of the little normal at that point? What's theta going to be for every single dA on that closed surface? Right. And what's the cosine of 0? 1. So in this particular case, it's just going to be the integral of 0 to a e dA. But since it's a sphere, what do we know about the strength of the electric field everywhere in that area around there? It's equal, yes? It's always going to be the same strength. So guess what we could do? What can we do with constants in an integral? We could take it out, because E is going to be the same on every single space of the surface. So since E has same strength everywhere on this Gaussian surface, we could pull that out and we could say it's going to be E integral 0 to a of dA. But what's going to be the integral of 0 to a of that dA? That's just the surface area of the sphere. So this is going to just equal E times the surface area. Oh, and by the way, when you take an integral over a closed area, you put a special symbol right here. And I should have done it starting over here. If it's over a closed area, you put a circle right here, indicating it's an integral not over just any old area, but over a closed area. So this is a special integral over a closed area. But this here just equals E times A, which is the surface area of the sphere. And what's the formula for the surface area of the sphere? Yeah?
Did we just do all of that just to get back to the original equation? Wasn't E times A?
Kind of. Kind of.
So, like, we couldn't just start with that. Plug in 4 pi r squared for the area.
We could, but we were looking at it in a broader sense so that we can handle future cases. But you got it. E times A. So this tells us how much flux is going through that sphere. Now here's where it gets interesting, people. Let's say I choose another area. Let's say I choose this area over here. This closed surface area, this sphere. Remember, it's three-dimensional. How does the amount of flux going through that sphere compared to the amount of flux going through the first sphere? Remember, flux is like the number of field lines, yes? Let's count. How many field lines are going through the first one? right, so do it in red. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9, yes? All right. How many are going through the green one? 1, 2, 3, 4, 5, 6, 7, 8.
You missed the other ones up top. There's a little in between the mini. The little mini one.
Oh, that one?
Yeah, you missed that.
All right.
That before.
All right, well then, anyway, it's the same. The amount of flux is the same. And what Gauss realized is the amount of flux going through a closed surface depends on one thing. The source of the field, which is Q1, the charge inside. And that's what Gauss's law basically ends up saying. That, look, if you take any closed surface, the amount of flux going through that surface depends on one thing. How much charge is on the inside? And we could actually take this one step forward, because look down here. If we continue to go with this, we already derived the electric field strength out there. What's the electric field strength on that surface there, that first black surface that we drew? 1 over 4 pi epsilon 0 times
Q over R squared.
right? So in this case, it's going to be Q1 over R squared. There's your E right there, yes? And then, what else do we have? 4 pi R squared. And how much electric flux is going through that surface? What is it? Q over epsilon 0. It turns out that the amount of flux going through any closed area depends on one thing: how much charge is on the inside. And that's Gauss's law. Yeah.
But the actual equation, like the answer you just got, like it would change for different outcomes.
No.
But I mean, like, yeah, like the physical number would change.
No, because the R's canceled out.
Oh, yeah. So E is indirectly proportional to the area, right?
And in the end, the amount of flux is the same for any closed shape. And it doesn't even have to be a sphere. It could be a regular old potato sack. The amount of flux going through that sack is just going to be equal to the amount of charge over epsilon 0.
But like not like a what's not a sphere, then the area is not 4 pi r squared.
Right. But if you went back and did an actual integral,
Oh, it'd still be the same.
it still works out to be the same.
If you said for a sphere, but different sizes of the same center. Yeah, that.
Any closed area, any size, is going to have the same amount of electric flux going through it.
No, I think it's actually Q over 1 over 4 pi k.
Finish graph.
It does.
Oh, yeah.
So that's Gauss's law right there.
No, I think it's flux equals 4 pi k.
That would work. You gotta let that go. Now, a lot of times we don't even care about the amount of electric flux. A lot of times we just use this right here to solve for the electric field strength. And we don't even mention like the word electric flux. We just solve that integral, and we know that it's equal to the amount of charge inside divided by epsilon 0, and we can use that fact to solve for electric field strength. So the first one that we're going to use this for is something very simplistic that we did right at the beginning of the unit. Go ahead, Max.
So before we found like units for the flux and whatnot.
Yes.
But in the permittivity of free space at epsilon 0, does that have units?
Yes.
Oh, so it's just like
You want the value in the units? It is 8.854187817 times 10 to the negative 12th coulombs squared divided by parentheses Newton times meter squared close parentheses. That's epsilon 0.
What do you use that set?
All right, so let's look at an example. So we have a hollow spherical shell, radius r, with charge q uniformly on its surface. Okay. So, and ultimately what we want to do, we got this hollow sphere, positive charge q all on the surface of this. And ultimately what we want to do is plot what is the electric field strength at various distances from the center here. And of course, to the actual shell itself, the radius is r, so that's going to be a key point.
it's gonna be like the gravity thing.
Yeah, we did this exact problem, even with electric field strength already. You guys had a quiz on this. Now we're just going to do it using Gauss's law. So let's say we choose our first Gaussian surface. It's a pretend surface that we imagine, and we use a closed surface, and we're going to just choose a surface inside right here. Right there, yes? And this is a lowercase r. Now, Gauss's law says that if we take the integral of E dA over that closed area, it's only going to be equal to the amount of charge on the inside divided by epsilon 0. Now, due to symmetry, we know the electric field strength is going to be the same throughout. And basically, we could factor out that E, and then it's going to be E closed area from 0 to A dA. And that's what we usually do when we're using Gauss's law, equals Q over epsilon 0. And that closed area there, that surface area, that's just going to be E times 4 pi r squared equals Q over epsilon 0. However, if it's a shell and all of the charge is like on the surface of the basketball, nothing inside, how much charge is on the inside there? How much charge is inside? 0. So basically, E equals 4 pi r squared, E times 4 pi r squared equals 0 over epsilon 0. And if you multiply this out, you end up getting E equals 0. Since there is no charge inside there, there's not going to be any net flux lines going through there, so the electric field strength there is going to be 0. So we know for the first system right here, it's going to be just like that. Now, what if we choose for our Gaussian surface out here? Very simply, Gauss's law says the amount of flux going through this imaginary closed surface that we just drew is equal to the amount of charge inside. But bam! So now we say here, oh, the amount of flux, which is E dA, is equal to the charge inside over epsilon 0. But again, due to symmetry, we know that the electric field is going to be the same value, the same strength all throughout. So we could pull out that E once again. And what's this integral once again going to be? It's just going to be the surface area of that sphere out there, which is going to be 4 pi r squared solve for E, what is E, the strength of the field out there, equal? 1 over 4 pi epsilon 0 times Q over R squared. That's what we got before, people. And we know here at R, and it's actually positive Q over R squared. And then right here, the value is 1 over 4 pi epsilon 0 Q over R squared. Right here at this point right here, it's big R.